Now, we were doing chromatography, and we were almost done with it. Okay. We talked about labeling the diagram, drawing the diagram, and we also talked about the RF value, which was the retention factor. So I told you that when you place a die, uh, different dyes are mixtures of different components. For example, green is a mixture of blue and yellow dyes. Again, well, if you remember arts, so you had primary colors and you made different colored substances using those primary colors. Now, so now the thing is, we were talking about RF value, and I told you that the separation happens because of the differences in the solubility of the dye. And if so, there's an absorbent material like a chromatogram or a filter paper, and water starts getting absorbed and starts traveling up that material, and it's going to carry the dyes. And if the dye is more soluble, then it would travel a longer distance. If it's not very soluble, it's not going to travel a very long distance. Uh, and we had, and just one second, we had people. I said, and we had the retention factor, which was the distance that was traveled by the dye divided by the distance that was traveled by the solvent. Okay? And I told you how those distances were measured. They were always measured from the starting line. You always have to remember not the solvent level, but the starting point. That is the place where you actually placed the dye. And from there, you would measure the distance of the dye. For example, for the blue dye, there's going to be an RF value distance traveled by the blue dye divided by the distance that is traveled by the solvent, which would be up to the solvent front. So, and that's how you're going to measure the RF value 2 divided by 5, and it will give you zero point 0.4. So the value is always between 0 and 1. And remember, if it's closer to 0, that means dye is not very soluble and covers a smaller distance. And if it's closer to 1, that means dye is very soluble. So you have to remember that idea. And if it's zero point 0.5, then uh, that means the dye travels half the distance. Okay, so remember what those RF value mean. Zero point 0.1, that means it's traveling a very small distance. Zero point 0.9 means that it's traveling a very large distance and it's close to the top. Zero point 0.5 means somewhere at the bottom, okay? In the middle, sorry. So, and I told you to do this experiment. So we were done with chromatography. Uh, we also talked about amino acids, that a lot of biological substances, they're not actually soluble. And since they're not soluble, uh, a lot of biological substances are colorless. So you spray the chromatogram with a substance that makes them colored, like a locating agent. So, anyways, moving on, ek, let me add one more small point, and that point is, let me add it over here. That small point is that if dyes travel the same distance, that means they are probably the same dye. In a chromatography experiment, if dyes travel the same, I said those who had missed the class yesterday, I mean, I did, I think, upload and send you the video. So if dyes travel the same distance and have the same RF values, so that kind of indicates that they are very likely to be the same dye. So if one person does an experiment and measures an RF value, if some other substance, other person in some other country does an experiment and measures the RF value, and the RF values come out to be the same value, that means they're doing the experiment with probably the same dye. Um, One last separation technique. If I had forgotten any, I'll come back to do the ones that if I had missed any. Uh, but most likely we have covered most of them. The last one that we're going to do is going to be called separation of gases by diffusion. Okay, by diffusion, Now you have studied diffusion. Diffusion was what was diffusion? Diffusion was that in liquids and gases, particles are randomly moving around. So if somebody sprays perfume in one corner of the room, then perfume particles are gaseous and they would start to move randomly and haphazardly in different directions. Plus, they're going to collide with gas molecules as well. So there would be, air molecules. There would be lots of air molecules. So these particles would be bumping into air molecules as well, and they would haphazardly be moving in different directions. You get just like billiard balls. If you strike a billiard table with a ball or with a white ball, all the balls go flying in different directions. So that's what's going to happen. Uh, so all these particles would randomly spread out. So we sprayed perfume over here, but the gas particles randomly collided with the air molecules, and they randomly traveled in different directions, and they would eventually be everywhere in the container. They would be everywhere, and the particles would spread. So we did diffusion in detail. Diffusion was the process by which particles would move from a region of higher concentration to a region of lower concentration, which basically means that they would spread out. You put an ink drop in water, the same thing happens. Put an ink in water, the particles randomly just move around, they collide with water molecules, and eventually they would spread around. They would just randomly and haphazardly spread around. So they would move from a region of higher concentration to a region of lower concentration. Now, in diffusion, when we were studying diffusion, we talked about uh, the rate of diffusion. And we talked about this thing that diffusion is, there are two factors that affect the speed of diffusion, which one is temperature. So if particles are at a higher temperature, then they diffuse faster. For example, you can smell hot food, uh, but the cold food that you take out from the fridge, you're not able to smell it because the particles have very less energy and they're not able to move around. But as soon as you microwave your food and it becomes hot, the particles, they travel much faster, and which is why you're able to smell it very very quickly. Uh, so temperature, higher temperature, diffusion is faster. So you have faster diffusion. But I'm more interested in the second, which is that lighter particles, they travel faster. So lighter particles would spread around at a much faster rate, and you can check the atomic mass or the molecular mass by looking at the periodic table, and you can measure the mass of the particles. Okay, we did a worksheet on this previously. Uh, so if you open the periodic table, the atomic mass is given. Every element's mass is given. So, for example, neon is 20, the big number that's in the periodic table. And let me keep a periodic table. You can just type AQA periodic table, and a PDF would open up. So I was interested in the mass of the particles. Lighter particles. So the big number with every element, that's your atomic mass. And we learned about calculating the atomic mass in previous classes. So, for example, you have neon. So what's neon is a gas. So neon is over here, and neon is 20. So neon has a mass of 20. Similarly, you've got, let's say, you've got carbon dioxide gas. That means the molecule has one carbon and two oxygen. So carbon is 12, and oxygen over here is 16, and there are two oxygens. So the mass would be 12 plus 16 times 2, because you've got two oxygens, and this would come out to be equal to, it will come out to be equal to 44. So you've done this before. You know how to calculate the mass of any gas, whether it's NH3. So just go and have a look at N and H. N is 14 and H is over here, that's 1. So it's going to be 14 plus 1 plus 1 plus 1, or there are three hydrogens, so that's 1 into 3. So it's going to be 17. Okay, so we did that. So anyways, so the thing is, particles that are lighter, for example, ammonia is a light particle. It only has a mass of 17, whereas carbon dioxide is kind of a heavy gas particle. It has a mass, it's much heavier. So lighter particles, they travel faster, or they spread around faster, or they diffuse faster. So how do you separate gases by diffusion? So the way you do that is, the idea is very simple. Let's say you have this pipe, and you've got a mixture of gases at one end. So I've got let's say the blue ones are ammonia, and the red ones are carbon dioxide. So they're all mixed together, and we also have neon. So the green ones are neon gas particles. So you have a mixture of gases, and you have this long uh, pipe, which is a hollow pipe, and you release the gases on one end of the pipe. So let me just mark this. This is neon is the green one. Carbon dioxide is probably the red one, and the blue one is ammonia. So what's going to happen is all these particles, they would randomly start moving around. They would start colliding with the walls of the container, and they would spread around, and they would start traveling from one end eventually to the other end. And let's say there's a collection device over here which is collecting the gases that reach over here. Can anyone tell me which of the three gases would reach the other end first? Anyone? Adil, Amna, Ashita?
Answer ammonia.
Okay, so ammonia is being the lightest of the gases. Ammonia is going to be the fastest. So it would travel the fastest because it's the lightest. So all the ammonia particles would be traveling very very fast, and they would be bumping and haphazardly moving around, and they would eventually reach the other end first. So you can kind of collect them first. So all these particles reach this end before the other particles. The second fastest would probably be neon. So the neon gas particles, neon was green. So the green gas particles would also be bumping with the walls of the container. They're moving around, but they're going to be kind of slower than, or slightly slower than ammonia. Whereas the carbon dioxide molecules would also be traveling, but they are the heaviest, so they would be traveling at a much uh, lesser speed. So you can have a collection device at the other end, and you can use that to collect the gases one after the other. The first one gas would be collected, that would be ammonia. Then you can collect neon. Then you can collect carbon dioxide. So is this clear to everyone? Turan, is this clear? Salim, Salama, is this clear?
Yes.
Chali. Now, so we're done with the separation techniques. Now we're going to do past paper questions. You can just give me a 1 second, and uh, and we did two things. We did apparatus, and we also did. So there's a worksheet that contains not kinetic particle theory. This one. So it has separation techniques both. Uh, so starting with these questions. And I'm going to send the worksheet, and I'm going to post this worksheet in the classroom as well. Now, a lot of things you haven't studied yet, but I'm going to talk about them. For example, you don't know what zinc carbonate is. Like, the first question is about the most suitable. Find the most suitable method to obtain zinc carbonate, to remove zinc carbonate from water. Now, I'll explain what zinc carbonate is. Zinc carbonate is insoluble. just like sand being insoluble. So you have a beaker full of water, and there are these insoluble zinc carbonate particles over here. So can anyone tell me quickly which method would you use to remove the zinc carbonate particles?
Filtration maybe.
Okay, so it's going to be filtration. Remember, insoluble particles are. I mean, there were lots of methods of separating insoluble particles. Just going back a bit. Uh, okay, so if you have an insoluble particle, remember, ignore that. I mean, right now, I'm assuming you don't know what zinc carbonate is. You don't know that it's insoluble. I'm going to add the information that's missing. Later on in later chapters, you'll learn about zinc carbonate. So anyway, so insoluble solid, you got filtration, you got decanting. Decanting was that you just allow the particles to settle down. You wait for them. You get like muddy water. You just wait for it so that all the particles they settle at the bottom, and you can just pour off the water from the top. You've got filtration where the large particles would get stuck in the filter paper, uh, and we and the third one was for suspension. So we can ignore that for now. Next one is an aqueous solution is colored. Which method of separation would show the solution contains ions of different colors? So how do you separate different colors? We just did that.
Chromatography.
Okay, so that's going to be chromatography, and you have got this one. Now this one is kind of a tricky question. Now again, it says the table gives the solubility of four substances in ethanol and water. So you've got if you don't know what ethanol is your normal spirit. It's You've got ethanol swabs for wiping your wounds. It's a disinfectant. It's present in hand sanitizer, so it's also a solvent. Remember, it's a liquid, just like water. Uh, so you've got two solvents, and a mixture containing all four substances is added to ethanol stirred. So you've got four substances. Let's call them A, B, C, and D. We don't know what those four substances are. They haven't named them. Uh, so you're seeing a mixture containing all four substances is added to ethanol, stirred, and filtered. So what is he doing? He takes ethanol. Let's say he takes it in a beaker. He adds all four substances. He adds A into it. He adds B into it. He adds C and D into it. So it could be all sorts of substances. It could be marble chips. It could be sand. It could be normal table salt or sugar, whatever A, B, C, D are four substances, and he adds it into ethanol. So that's the first thing. And so then what he does is he stirs it. So maybe A is soluble, so A would dissolve, or B is soluble, or C is soluble. So some of them would dissolve, some of them will not dissolve. So what he does is he filters it. Now when he So it's going to pour it into through a funnel into a filter paper, and he filters it. So the insoluble substances out of A, B, C, and D would get stuck over here, and the soluble ones will not be filtered. Okay? For example, if something is soluble, completely mixed, it's going to pass through the filter paper. If something is insoluble, it would stay behind. So, for example, if you had sand would get stuck over here. But the salt, like a table salt, would be soluble. It would come out as a filtrate at the bottom. Now he's talking about. So that's the first step. This is known as the residue. And then he says the solid residue is added to water, stirred, and filtered. So he takes the solid residue. So this is what he's doing now. He takes the solid residue, takes another beaker, adds it to water, and this time he's adding it to water, and he stirs it and he filters it again. So once he mixes them, he then passes it through another filter paper and he filters it. So something would, if it's insoluble in water, it would stay behind as a residue. Otherwise, if it's soluble, it would come out as a filtrate. So he's saying the solid residue is added to water, stirred and filtered. The filtrate is evaporated, leaving a white solid. So this is the filtrate. And he's saying the filtrate is dried, so it leaves a white solid. Uh, and he's saying which is the white solid. So remember, repeating everything. He mixes ABCD four substances into ethanol. Some of them would mix, some of them will not mix. If they don't mix, they're going to remain in the residue over here. If they're mixed, they're going to pass right through it. So, so he's taking the residue. So is this substance soluble in ethanol or insoluble in ethanol?
Insoluble.
Okay, so it's okay. So it's going to be insoluble, right? Then whatever substance is over here, the residue, he puts it in water and then he filters it. But this time it goes into the filtrate. So is it soluble in water or insoluble in water?
Soluble.
Soluble because in
Soluble.
water, okay, that means after adding to water, it passes straight through. So that means in water it dissolved. So it is soluble. So the answer is going to be B. Okay, so uh, again, just for clarity, I'm explaining this again that you added the four substances. Uh, the substance that you got over here was actually stuck over here in this residue. I mean, this is what he said, that the solid residue is then added to water. So he took the residue, which means that whatever substance got stuck over here, that wasn't actually soluble in ethanol. Then he took that substance and added to water, and this time it dissolved and it passed straight through. So that means in water it was soluble. So is this one clear to everyone?
Yes,
Yes.
sir.
So next is again a fruit drink colored orange. It has red and yellow coloring agents. So which method would you use?
Chromatography.
Okay, so just when you see coloring agents, that's basically chromatography happening. Now, this question, I want to discuss this question. Now, remember, I told you that if two dyes travel the same distance or they have the same RF value, that means they are the same substance. Okay, this is what I mean, I did write this somewhere. I think, okay, I wrote it over here. That if dyes travel the same distance and have the same RF value, that probably means they are the same dye. So, coming back to this question, so now he's doing four chromatographies. There's dye W, I mean W, X, Y, and Z. So there's W, X, Y, and Z. So he places four spots onto the filter paper, and the solvent would he dips one end into the solvent, and the dyes they spread upwards, right? So he's saying which two substances are pure. That's the first one, W. How many dyes make up W? That's one and that's one and two. So W is not pure. If you look at X, uh, and separation happens in this direction, different dyes would start traveling at different speeds. Uh, if you look at X on the other hand is a pure substance because even after chromatography, there's only one dye that's present in X. Like when the solvent started traveling upwards, uh, the dyes did not separate. That means there's only one dye in X. Okay, is this clear?
Yes,
Yes.
sir.
So similarly, why this one Z is also a pure substance, whereas uh, Y is made up of two dyes. So it's going to be X and Z. Answer would be D. That these are the pure substances, whereas Y and W are both made up of two dyes. And also remember that if dyes travel the same distance, that means they are the same dyes. For example, this one, and this one, they're traveling the same distance. So that means they're probably the same dye. This one and this one are traveling the same distance, so they're probably the same dye. Anyway, so this is this. Next one is you've got chromatography and fractional distillation can be used to separate compounds. In which type of separation is the thermometer needed for checking that complete separation has occurred? Do you need thermometers in chromatography?
Fluid.
So anyways, you need thermometers for fractional distillation. Uh, anyways, fractional distillation. We did fractional distillation. एक second. I think this was fractional distillation, and fractional distillation was for two liquids which are soluble in each other. That is when you use fractional distillation, and the two liquids must have different boiling points, so that one evaporates first, and the second one evaporates at a later time at a higher temperature. So, so it's going to be fractional distillation of different colored liquids or colorless liquids.
Colorless liquids.
Okay, because for colored you use chromatography. And how did the thermometer help? The way the thermometer helped in figuring out whether separation had occurred or not was that if you have ethanol in water, the temperature when the change of state is happening, it becomes constant. So initially, when the temperature you're heating it and the temperature is increasing, the temperature would become constant at 78. The thermometer is showing which substance is going into condenser. So it's going to become constant at 78. And as long as the thermometer is stuck at 78, you know that ethanol is the one that's actually distilling. And once the temperature starts to rise again, that means all the ethanol present in the flask over here has already evaporated and it's gone. Now the other substance, which is water, that's the one that started to it has started to distill and it has started to evaporate and boil, and it's now being condensed at the other side. So the graph would clearly show you which substance is being received at this point. As a next is as a which mixture can be added by adding water, stirring, and filtering. Uh, Now again, you don't know any of these compounds. Assuming you don't know any of these compounds, I'm just going to talk about the solubility of these compounds. The first two are soluble. Okay, let's call them X and Y. So they're soluble. You take a beaker, you add water. Now there's X and there's Y. So you add water, you stir, and both of them are soluble. So both of them would mix in the water. So would filtering help or not? Would filtering separate them or not?
No.
TK, it won't, because filtration doesn't work for soluble substances. You need insoluble particles, only they can be filtered out. So the first one is not going to work. The second one is you've got copper and magnesium, and they're both insoluble. So there's insoluble. There's I mean copper is wire. It's your normal wire, so it doesn't really dissolve. So in this case, what's going to happen is, let's say you add X and Y, copper and magnesium, and what would happen is that this is a piece of copper, this is a piece of magnesium. Now, and let's say there are lots and lots of tiny pieces of copper and magnesium, right? So you add water, and they're not going to dissolve. Nothing would happen to it. Like you add a copper wire to water, nothing should would happen to it. It's not going to dissolve. So you filter it. Now, if you filter it, the residue would contain the copper and the magnesium. Both are going to get stuck over here. So would they be separated or not?
No.
Okay, they won't be because they're still together. Okay, and just for because you're starting this, I just to introduce these elements. Okay, because later on we're going to study this. So copper is this pink kind of pinkish metal. Okay, that's You make wires out of it. I mean, you can call it golden brown, but it's very pure copper is kind of pink. And magnesium is also a metal, and it's like a gray metallic, like what normal metals look like. Normally, metals look like grayish, shiny and grayish. So these are your two metals. And anyways, no separation would occur. So then you've got diamond and graphite. Now diamond, I mean, you already know what diamond is. Uh, Graphite, diamond and graphite are actually, we're going to study them later, but diamond and graphite are kind of they're both carbons. Diamond is obviously diamond, and graphite is the black soot that's left when you burn wood. ठीक है, you can call that graphite. So this is like graphite. It's not soluble. Uh, so it's the black substance that's usually left when you burn something. So this is graphite, and they're both insoluble. So something similar would happen, which happened to copper and magnesium. Like you add diamond and graphite, both diamond and graphite particles would be stuck over here in the residue. They won't be able to pass through the filter paper. So when would separation happen? Separation would happen in this last one. Okay, again, you don't know what AgCl and sodium nitrate is, but I'm going to tell you that this compound is insoluble, right? Whereas sodium nitrate is soluble. So this one is soluble. Um, so let's say there's X and Y. Now one of them is soluble. So that means one of them would would dissolve completely in water, and it would become part of the filtrate, which is going to be sodium nitrate would pass straight through. Sodium nitrate is like your normal table salt. It's like NaCl. Like if I show you what sodium nitrate is, so it's exactly like your normal table salt, but it dissolves just like your table salt. Anyways, for now, just a brief introduction would be sufficient. Don't want to go into detail about these compounds. Silver chloride, on the other hand, is insoluble. So the AgCl or silver chloride would be stuck. I mean, this is silver chloride. That would be stuck at the top. So separation is going to be possible in option D. Is this clear?
Yes, sir.
Okay. Just remember, right now, don't get confused with these compounds. We're going to study these compounds much later on. So I'm adding all the information uh, that is sufficient to just answer the question. Okay. So is this clear to everyone, Salim? Asidas, Lama, is this clear?
Yes, sir.
Yes,
Yes,
clear.
sir.
Okay. As the next one is which method can be used to obtain crystals from aqueous copper to sulfate, and that's basically evaporation. Okay, we did crystallization. How do you form crystals? There were two. I told you there were two ways to evaporate. One was you simply evaporate everything to dryness, and the problem with that was that all the water molecules would leave very quickly, and the particles would not get enough time to form crystals. The other one was crystallization, where I told you that you evaporate some of the water and then you allow the particles to kind of join up, cool gradually, allow crystals to form, and then you filter out the pure crystals that are formed. So crystallization was kind of a slower process where you gave the particles time, and you don't evaporate the whole thing. You just evaporate some of the water molecules, so that the water molecules get out of the way and the particles can sort of join up with each other and form these big crystals. But both of them are basically, they require evaporation. One is complete evaporation, the other one is just partial evaporation. Next one is the pH of some aqueous sodium hydroxide is measured. The solution is then distilled as shown. Uh, I'm going to ignore this for now because pH. I mean, that comes much later. So let's ignore that question for now, because I would have to explain the whole pH thing, which you wouldn't get right now at least. Anyways, next one is diagram shows a chromatogram obtained from three sweets. I mean, this is an oversimplification. So this is where he did three sweets. So this is where he's. I mean, this is the spot where he's placing the sweets, and he dips them in a solvent. So the solvent starts traveling upwards, and the dyes start to separate, right? So he's saying how many different red dyes are present in the sweets. Now I told you specifically that if a dye travels the same distance, then that pretty much means that they are the same dye. So for example, this red dye over here and this red dye over here. I mean, the two completely separate chromatography is happening, but this red dye is also traveling the same distance, right? And this red dye is also traveling pretty much the same distance. So that means they are the same dye. Is that clear?
Yes, sir.
Yes, sir.
Yes.
So if anyone has any questions, they can ask. Similarly, you have so that's one type of dye. Let's call that dye one. Okay, so that's one type of red dye. Both of these red dyes are basically the same dye. They're traveling the same distance. On the other hand, you have this red dye, this red dye. I mean, they're two separate chromatogram. This one travels this much distance, and this one also pretty much travels the same amount of distance. So that kind of means that this red dye and this red dye are kind of the same dye. So that's the second type of red dye. So basically, how many different red dyes are present in the sweets? So it's basically two types.
Two.
Okay, is this clear?
Yes, sir.
Okay, so next one is some chemical compounds are purified by recrystallization. How could you? I said there was earlier we studied how do you check for the purity of a substance, whether it's pure or not.
The melting point.
Because it's you take the melting and boiling point. So pure substances they always have a very fixed melting point and boiling point. For example, you have water. It always melts at if it's pure, if it melts at zero and it boils at 100. But if it's impure water, then the boiling point and melting point would be slightly different. And this is what they're asking over here. So previously, I mean, this isn't part of separation techniques, but I had told you that when water has impurities dissolved in it, normally its melting point is 0 degrees centigrade and it boils at 100 degrees centigrade. But when it's impure water, what happens is that the boiling point actually becomes sorry, the melting point becomes less than zero. Water starts to melt easily, and the boiling point becomes greater than 100. So it might be 101, it might be 102. The melting point might be lesser than zero, would be -1, -2. So the only option that actually fits this one is D, I think. You can always remember this, that especially for water, that pure water melts and boils at a very fixed temperature. But as soon as you add an impurity to it, any impurity, you add sugar to it, you add salt to it, you add sand to it, whatever you do, its melting point drops and its boiling point increases. Okay, clear?
Yes.
So I think we'll continue with more questions. I'll post this as an assignment on the classroom group, okay? And try and go through the questions. Try and complete the previous all the previous worksheets over there. Take his assignments. Try and go through them. Probably tonight I'll post this. Jenny, let's.
Yes, sir.
Yes.
I think you've already posted the assignment for this for like Monday. So which questions do we need to do?
I said that I'll tell you. I'll give you theory questions, which are somewhere. That's these ones. So I'll edit that and I'll tell you what the pages are. Okay.
Thank you, sir.
Okay. Then. Take care, everyone. Allah Hafiz.